Okay, so now that we know that the slopes we're seeing should be positive in this quadrant and this quadrant, negative in these other two. I'm going to erase all those because it's going to really clutter up the figure if I don't. And we know that the slope should be 0 anytime x and y are 0, and then sort of decrease from there, or sorry, increase from there. Actually, you know what? I think it'll be okay to keep those things. I'm going to go ahead and do it. I don't want you to lose track of where all this different information came from. Okay, so we know that, and then let's pick a new color. Let's say that. So as we move away from 0, we'll get more slope in x. And the same thing in y. So no slope when y is 0, but then more as we get further and further away from 0. Those are the rules that we learned from plugging in different values x and y into the f of x, y, 0.2x. Now I'm just going to go ahead and draw this. So I should have no slope anytime x is 0. So that just means horizontal lines. And anytime y is 0, I should have the same. I'm going to draw these arrows kind of sloppily because I'm not very good at drawing, but they should all be the same size if I was being careful about it. And then I should have the most slope when x and y are really big. So in this first quadrant right here, I should have a really steep positive slope when x and y are large. Like so, 0.2 times 10 times 10 is 20, I think. And then 0.2 times negative 10 times 10 is negative 20. 0.2 times negative 10 times negative 10 is again positive 20. I really should have checked that that was true, but I really think it's 20. So our steepest slopes are going to be kind of on the edges. And then we're going to start with these horizontal slopes when x and y are 0, but they'll slowly become less flat as we move further and further away towards that steepest point. Kind of like that. Same idea in the negative side. We've got very steep, far from the origin, becoming less steep as we get closer to the origin. Like that. So if my work here was not indication enough, the artistry here doesn't have to be great. Just communicating the general idea is what's important. And we're actually going to look at computational tools that make this a little bit easier later. But all I'm trying to do when I draw these different things is communicate that I have very steep arrows far from the origin, very shallow arrows close to the origin, and the positive or negative trends depending on which quadrant I'm in. That's a rough picture of our direction field. Now, the way we use this is kind of this last sentence right here. The direction field's arrows indicate the, quote, direction of a solution from any point. So what these arrows are showing us is how the solution moves. So, oops, better erase that for anyone who reads the notes. I'm going to tell you here how we use the direction field, and then we'll go back and use it in a second. So using the direction field. what's going to happen is, given a field, we can start at any point x0, y0, which corresponds to initial condition y of x0 equal to y0 in an initial value problem. And starting from that point, we would follow the arrows to sort of sketch or approximate the solution y of x to the differential equation, but specifically from that initial condition, so to the initial value problem. And so let's go ahead and try that on this picture. I'm going to use this red color again. And so let's say that this is my initial condition, x0, y0, right there. Somebody told me that my initial value problem, oops, here, we'll do that. We're going to go back to the other page and use this initial value problem for dy dx equal to 0.2 xy. And we're going to use initial condition y of -10 is equal to -10. And I'm going to stop like pointing out x0, y0 later. I just think that it's good to be clear about the notation these first couple times we use it. So I had this initial value problem with x0 equal to -10 and y0 equal to -10. And so I went to my direction field and I started at x0, y0, -10, -10. That little star is where I started. And all I do is I follow these arrows. So I start right here and I'm kind of following that downward arrow. And then I kind of just follow the next nearest arrow. Again, this isn't perfect, but general trend of the arrows tells me that I would eventually do that. Didn't draw that with a very solid line, but that's what it's doing. And so this pink line that I just drew is the solution to the initial value problem. Starting from that -10, -10, I see that it eventually goes through this, I don't know, 10, 10-ish place, and then leaves the graph because I didn't draw very much. We'll do one more here. For anyone who cannot see colors, it would be bad to just switch them. So we'll have that star, and then this flower will be our second example. An initial value problem could be dy dx equal to 0.2 xy with y of, let's see, oh, whoops, okay. Let's do y of -10 equal to -10 for real this time. I did -10 plus 10. That's my mistake the first time. And so this one starts actually at -10, -10. And so we kind of follow this upward direction and then down again like that. That's our solution y of x to the second example. So that was an example of generating a direction field and reading off of it. In practice, we can use computers to generate much better direction fields than what I'm able to draw. And in the next video, I'll actually show you that. I'll switch away from this app and open up a website that you can use instead. But we learn to plot them by hand. so that we understand what they are. But the most important thing is what we can learn from a direction field. And so in the next video, I'm going to show you an example that uses a computational tool that I'll give you a link to just so that we can see how that works real quick.